All right. I don't know if you have questions on search or not. I guess not. So in this case, we're going to actually go into a quick example of what quiz questions look like in terms of binary trees. I can't give you the exact quiz questions, but I'm going to look at some from last semester and try to give you sort of a rundown of what you'll be expected to know come quiz 5. And on Friday, I'll be getting into more detail on these, doing more of a better implementation of a binary tree, maybe without all the technical difficulties, and I'll try to squeeze in an application of it as well. So looking at, hold on, let me pull up last semester's quiz, and we can see it's going to be 2020 fall, and I'll give you kind of similar stuff, not the exact same obviously, but you can expect the same content is covered. Let's just get that up and running. I had it prepared before, but of course the thing crashed. So let's see it now. Yes. All right, perfect. So common questions for quizzes would be you're given a set of elements and a binary search tree, and you're told how they're arranged. So I'll put this in the comments in here. So let's say given an array, let's say 0, then negative 1000, comma negative 1001, negative 955, and that. Right, given an array, we insert into a binary search tree these elements. What does the tree look like at size 4? This would be an example of one of the quiz questions you might see on trees, binary trees, this sort of thing. The answer to this question, can anybody give it an attempt? All right, any ideas how we could go about doing this? We have this array. We insert this into a binary tree, same as here, right? This is just following the this constructor. We're just basically doing this. We're saying binary trees tree is equal to new this, and then in here we throw in those elements. So those elements will be 0, 51, whatever, right? So how will this tree look after we run this insertion? That's the question. And in terms of code, what it looks like is we're actually just calling this constructor new binary trees with the e dot 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 elements. This is essentially the same thing. How would you guys approach this kind of question? All right, well, maybe I'll give you guys a start on it, and then you guys could come up with further. So what we're actually doing is we're saying, you know, for, so what we're actually doing is we're saying for every element in this array, for, you know, int I colon array, tree dot insert or dot add I, right? That's what we're actually doing every time we do that. So we're asking what happens the fourth time. So what happens when we add the first 4 elements of this array? Or more accurately, what does the tree look like? What does the tree look like means what are the nodes of the tree? Now, when we're doing this, yeah, so one of you guys say 0 is root, so it goes 0, then to the 351 to the right, so 351, and negative 1001 to the left, seems legit, because that's from the order we add them in. But is that the, yeah, to the left of 1000, okay, I see. So it would actually be more like 1000 on this side. So could you go on the mic and maybe explain how you came up with this solution to this question?
Negative 1000 would be to the left and 351 would be to the right. And then the next one would have to have depth 2 then, since it came after the first 3. And it has a value less than negative 1000, so it would have to be to the left of it.
Okay, that's great. Yeah, so we're following our binary search tree rule. It's the same way that this algorithm works. The search algorithm, we're basically following that, and we're following the add algorithm. and we're seeing exactly how it's going to happen. These questions can seem kind of confusing to you, especially with the first 4 elements. This stuff here is here to trick you and to try to confuse you as to how to draw this tree. But in reality, it is just as simple as running the algorithm in your head, and it's the kind of algorithm which I think can be pretty easily done, like in mental math. You just see the first one we had is the root. Is the next one smaller or bigger than the root? That determines which side it goes on, and then that goes from there. Like it follows from that relatively trivially. So we have that kind of question. Now that's probably going to be the least spicy type of question on the quizzes. So if you have questions about how to do these kind of questions, maybe I can do another example, but they're pretty straightforward. As long as you understand how add works, you'll understand how these work. Now, the next spicier kind of question we have will be this. We'll say, given a tree, let's say we draw it out. Let's say A, here we have B, C, D, E, F, G. Now, F, G, and everything are not necessarily, like F, G are not necessarily their actual, like letter values. They're not sorted by those. That's just some arbitrary nodes, right? So, the question might be something like, oh, actually, G here, I'll do something else, like H, I, J, K. So now the question will be like, how many steps are taken to search for J? So how many, like, what is the depth of the recursion to get to J? Maybe would be how it could be worded or something like that. So what would the answer to this be? How would you guys think about this? So what is the depth of the search for J? How many times does it recurse? Count the number of edges then? Yeah, okay, so can you explain what you mean by that?
If we know if we know what J is, the value, we can directly go for it instead of looking in every branch.
Yeah, well, we know that we're going to do compare to, right? So we're going to say A compared to C compared to whatever, right? And we can assume that this tree is correctly ordered. We're just running the search algorithm. Right, and I'm sorry. Normally, I would want to use letters that are like alphabetically properly sorted, but it's just that I like didn't want to think about how I could, like, you know, run the adding algorithm. So we're just going to say that these letters are not being compared alphabetically; they're being compared by some arbitrary comparison. And like, oh, how would the search algorithm look on this? The trick about that is that we actually don't care what the values of these things are. What we care about is like what is the path that this algorithm would take in finding an element that was stored here. And the answer to that would be, well, this element is going to obviously be larger than A, larger than C, larger than G, so it's always going to go to the right. Now, how many times does it go to the right? Well, it goes to the right 1, 2, 3, 4, 5, 6 times. So we have to recur 6 times to get to J. That would be a traversal, or like a search traversal to get to J. Right? Would that make sense to you guys? Isn't it 5? Well, if we count from the root, then it could be 5. If we count from there, it could be 6. I would say 1, 2, 3, 4, 5, 6. If we count that we start at the root, if we count our initial call as a like part of our recursion, and if we don't count our initial call as part of the recursion, then yes, it's 5 because this actual recursive method is actually called 5 times. You could probably argue for either one. So this is not a great like quiz question. It's probably not one that would be asked, but the same concept applies, right? That's generally how it would run. Now, with this in mind, what would actually be the upper bound of the time complexity for finding an element in a binary search tree? So, question, what is the time complexity? Is the time complexity of finding an element in a tree? You say O of n, where n is the depth. All right, that's a great answer, but could you explain to me why is it useful to have this be O of n? Isn't it also O of n in a linked list? Like when we search in a linked list, isn't also going to be O of n complexity to find any element? So why is a binary search tree called a search tree, and why do we use these things for searches, even though it's O of n? How could it be O of n if, we have this less than or greater than rule? You're correct that it's O of n, but I'm just asking, like, how did you come up with it being O of n when this occurs? Because really, when we're creating like a linked list, right, we can just add to the tail, like it's a stack. We can just push to the stack, and we can say that, the tree t is equal to new tree, or like a stack is a new stack, and we just keep pushing to the stack, and that's going to be O of 1 to add, which is faster than a binary tree, and it's going to be O of n to sort, or to traverse through. Okay, so we say it's in one worst case where there will be one long branch. Exactly. So we say it's going to be O of n. Now the follow-up question, of course, is why do we care about trees if it's still O of n? Well, the answer is that usually it's much better than that. So answer is that it's O of n when the tree is awful, when the tree is unbalanced. Unbalanced. It has a long chain, and it doesn't really use its properties. So that's when the tree looks like this, like A, B, C, D, E, then, dot, dot, dot. Like, let's say, yeah, right? So this would be an unbalanced tree. So this will be O of n. This is O of n. But now, what would be the time complexity if we had a balanced tree? So if the tree was something like this, like 1 or 0, then here we have like negative 100. Here we have, negative 101. Here we have negative 99. 99. Here we have, 100, 99, 101. How long would it be this? It would be here. So in this tree, in this nice tree, it would take O of log n, where n is the number of nodes. Yeah, O of log number of nodes. So this, can you tell me why is it log number of nodes?
The maximum depth will be restricted by, because if, for example, each node has 2 children, then the maximum depth will decrease each time. I don't know how to explain it, but it's like a factor divided by 2 to the k.
Exactly, you're right about that, because I'd say the explanation I usually give is that we have each one has 2 children, right? So to fill up each level, we need 2 to the number of nodes here. So here for size 1, we've got 2 to the 0 nodes and depth 1, right? Here we've got for size 2, we've got, let's say 2 to the 1 nodes, or for depth 2, we've got 2 to the 1 nodes, 1 nodes, and depth 2, right? And then here we've got, for depth 3 is got 2 to the 2 nodes, and dot, 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 right? So now we've got depth 4. Depth 4 is going to be 2 to the 3 nodes, and then depth n will be 2 to the n minus 1 nodes. So what we actually mean is that to get the number of the depth from a number of nodes, right? So our time complexity is like this. Our time complexity for add, remove, search is equal to O of depth. O of depth, right? But so how do we get, but we always put time complexity in terms of size, right? So our big O notation is not O of the depth. Our big O notation has to be O of the size. So what we have to say is that depth is equal to, depth is equal to, or depth to the 2 minus 1 is equal to size. But then we can also say that the inverse operation of that will be the depth, and I'm going to drop the minus 1, so drop minus 1 because it just came up from starting depth at 1. And then we say that size, or depth, is equal to log base 2 of size. Right? Does that make sense? Here, if I start this at depth 0, it's going to be just 2 to the n rather than 2 to the n minus 1, and maybe I should do that just to make it more clear. So depth 2, depth 3, depth n is going to be 2 to the n nodes. There. Now it's kind of more logical. Do we understand kind of why that is then? Like, why is it... Do we understand why it's O of n in the worst case, but it's going to be O of log base 2 of n in the situation where our tree is nice and well-behaved? All right. Now, later on in the course, we'll learn how to make trees which actually balance themselves, and that's a big thing in Comp 251 as well. I don't actually know if we'll cover it in Comp 250, but we will be doing it in terms of O of n. Just wondering, if we were asked the time complexity of a B tree, you will be asked about time complexity of a B tree, and in general, you would say O of n for things like add and for things like remove, because it's not specified the tree is well behaved. So here's a question that might throw people off. If we say, question, what is the time complexity of add? Is the time complexity of add for a balanced binary search tree? Now, what is the answer to this one? O of log n. Log n. Right? That's because we know it's a well-behaved tree. We know it's a well-behaved tree, behaved tree as above. Right? Now, if I just said, question, what is the time complexity of search for a binary tree? Asking this, well, what's the answer? It's log n. Well, not quite. The difference here is actually between the idea of balanced and just binary tree. When we just say binary tree, it's going to be O of n, because technically, in the worst case, it can look like this. And by this, I mean like that. Right? And if it looks like this, that's going to be O of n, because we're just going to have to traverse through this entire list and get to the item at the end. If we're technically looking for nth letter, then it's just going to be traversing a linked list, and it's going to be O of n, right? So that is kind of the confusing part of time complexity for a binary tree. Now, I would get into more of these quiz questions right now, but those actually need you to understand how we can use stacks and queues in conjunction with a binary tree, rather than just doing binary trees purely. So next time, what we'll do next time, we'll have stacks and queues mixed with trees, used for traversal. We will have more questions. We'll have remove. We'll have application of a BST, and we'll have a, what else did we not cover? Anything else that I haven't covered today? Today, that will be on the quiz. Now, a couple final notes about the tree. So trees technically don't have to be binary. Trees may have n children per node, but binary trees have 2. 2, that's why it's binary. right? That's one thing. The next thing we want to say is that a graph, which is not what we're doing here, but a graph is a data structure with links, and a tree is a type of graph. We don't need to know more on that. It's just in case somebody in a quiz question or somewhere else says something about a graph. That's what we mean by that. Then another thing we want to cover will be the different types of search, which we will cover more next time. But I'll give you a quick peek of the slide anyways. So there we are. We go. The root is of course each node, and we've got in-order traversal, which goes through each of the roots to get them in sorted order. We've got reverse order traversal, which goes through in the inverse of the in-order traversal. If we use a stack for in-order, we can use a queue for reverse order, and then we can use the same algorithm. And just if we push to a stack versus a queue, we can get it in opposite orders. We have a search algorithm, and search will use the property, as we did today, to find each element. Breadth first will search through the width of the tree, trying to get through each level of depth before it goes to the next one. And depth first will go to the deepest possible depth before iterating to the next. That should be most of the content we care about in terms of those trees. A quick note that the next assignment will also be heavily about these, so it's good to understand a good mastery of the trees. Usually every semester the tree assignment is the hardest one, so it is something to be prepared for. But anyways, hopefully it shouldn't be too bad if you guys really understand the content. And are there any final questions about anything?